Okay, since you were so nice to wait for me, I will actually tell you how I met Brendan. It was about 7.5 years ago or so. And I was in academia, as you heard. I have a PhD in computer science. And my entire career was really going towards being a professor. So I've worked all my life being a professor. I went to different schools. I got every degree available in my field. And I was trying to write compilers. And back then, in the beginning, I was writing Java compilers. And then I had the idea to write a JavaScript compiler. And the entire academic field that I worked for thought that that's a really dumb idea. I submitted paper after paper showing how you can make JavaScript go really fast. And everyone told me that I'm solving the wrong problem. That problem was already solved. Someone invented Java and typed languages. All you had to do is use Java instead of JavaScript, and then you wouldn't need compilers for JavaScript. So I couldn't convince anyone in my own field in academia to do JavaScript compilation. I ran into Brendan. This was around the time when Chrome was about to come out, and we knew that performance would kind of heat up in the web. And Brendan hired me to Mozilla to write a compiler for JavaScript. And we together released the first commercially available JavaScript compiler a couple days before actually Chrome came out. So that's how I met Brendan, and it was meant to be a very short stay. I was originally planned to come up for 3 months. We estimated you can write a compiler for JavaScript in 3 months. And somehow I ended up never leaving. All right, but now let's talk about Java and JavaScript some more. My talk today is going to explore why we are doing Java and JavaScript, but also I want to be a little bit technical and show you a little bit of the details of Java and show you how you can implement Java in JavaScript, and some interesting things emerge if you do that. First of all, let me explain why we would do this. Why would anyone in the year 2014 try to write a Java VM for JavaScript? Java we almost successfully removed from the web stack. Today, it's very, very rare that you're running across Java applets. It's mostly banks, I think, that use it still for security and login mechanisms. The reason is really this here. You might know that we started bringing smartphones to market about a year ago, Firefox OS. And Firefox OS is targeting parts of the world that have a lot of people who currently have a feature phone, and they're looking to get their first smartphone. So the device we're seeing here is actually a device we launched about 2 months ago in India. The price for this device is around $30 US. So it's about the cost of like a lunch in San Francisco. You can get a smartphone. And this thing is completely powered by HTML5. So everything that you see in this phone, everything that runs on the phone, all the apps, the UI itself, everything is written by HTML5, in HTML5. One problem that we ran into is that these over-the-top messaging apps like WhatsApp are very popular all around the world. And it differs a little bit where what is popular, but you can see that the parts of the world where we particularly are focusing on with Firefox OS, such as here in LATAM, but also Asia, in those parts of the world, there are specific messaging apps that are really popular. And it's very hard to convince a maker of this messaging app to make an app for HTML5 in some of these cases, because there's not a lot of devices out there where today you can only bring HTML5 content to. So on Android, you can run an HTML5 app, but you can also run an Android app. So these guys have all written Android apps. For us, there's no Android in our stack, there's no iOS, there's only the web and HTML5, so we needed somehow a way to get these apps to run in our platform. In some cases, we were able to convince them that HTML5 is the future and they should write an HTML5 app for the platform. Line, for example, did that, but a couple other guys didn't do that. And if you look at this graph, this data is about a year old, but it shows that in some parts of the world, some of these messaging apps are very, very popular. And if you don't have them on your phone, nobody's going to buy it. Okay, down here, for example, in many parts of LATAM, if you don't have WhatsApp, it's really difficult to explain to someone why they would want to buy your phone. So we needed a way to have WhatsApp on this device, even if WhatsApp was not willing to make an app in HTML5 just yet, because when we started last year, we started with 0 users. So there's basically 2 things you can do. One, you can go ahead and try to just write your own WhatsApp implementation or line implementation. We did that, and some of those you can get in the marketplace, but people often ask specifically for WhatsApp. So they go in a store and want to buy a phone with WhatsApp, or with Line, or with Viber. And in these cases, people in the store would say, well, it doesn't have WhatsApp, but. The moment you start a sentence with, it doesn't have WhatsApp, the person basically immediately doesn't want the phone anymore. So to solve this problem, somehow we have to get WhatsApp onto our phone without relying on them making a WhatsApp version until we have enough users that people write naturally software for HTML5 as well. That's kind of the whole idea what Mozilla is all about, right? We want to try to make HTML5 as successful on mobile as it's today on a desktop. It gets even a little bit worse because the main competition for Firefox OS phones are these things, feature phones. So for the price range of the very entry-level Firefox OS devices, that's kind of the competition you can get. Something like Nokia feature phone with a dial pad and a small screen. These things actually, many of these messaging apps are available. So this makes the situation for us a little bit more tricky, because on the thing we compete with, which is so much worse in hardware, and it doesn't have proper web experience, doesn't have a touchscreen, but it has WhatsApp. So people go in the store and they want a thing with WhatsApp, and then they get this here and not the smartphone. At the same time, though, this is actually also a nice solution because, as I said, these things run these messaging apps. So the idea we were looking at, how can we take these messaging apps that are designed for these feature phones and run them on Firefox OS? These things, of course, run Java, right? In case you didn't know that, if you ever have to install Java, and I hope nobody here is that unfortunate, when you install it, it tells you that there's over 3 billion devices, or 3 billion phones running Java. I'm not sure it's still true today, but it's probably roughly the right ballpark. There's literally billions of phones out there. Anything that's not a smartphone today tends to run Java inside of it. And it runs a very specific version of Java that's called j2me. And I will kind of explain where that fits in. Many of you have probably never seen this. That's not a problem. It's just, this is old stuff. This is like, I pulled this, you can see how bad the fonts are. This is like a 14-year-old picture. So this is what some thought the world would look like in the future, like 14 years ago. So basically the idea was that everything is Java, all the way from Java cards. This is SIM cards in your phone, for example, on the very right side here. And then there's these lightweight versions of Java. This is the micro edition or limited device edition of Java. And then here's the grown-up Java on desktop and on servers. Of course, today this totally looks different, right? So the only place where Java really survived is in SIM cards. That's still Java today. And then on the very far end here, in enterprise and servers, there's still some Java. In the middle of it, it's more or less dead. The particular piece we care about is this one here, the limited configuration of Java that runs on these feature phones. The VM that was built for that is called KVM, or the kilobyte VM. That meant to express that these things are designed to run with relatively little memory that you have available in these feature phones. So there's a couple different ways how we can go and implement a Java VM in our phone. To explain that, I have this architecture diagram here of Firefox OS. I have no idea what the Japanese characters mean, in case you wonder. I just found this, and it's really cool graphics. I also have no idea what the ice cone means, but it was really kind of funny, and I liked the picture, so I decided to use this. It does show the necessary things I have to show, so just ignore the Japanese characters and ignore the ice cream cone for a moment. So we have at the bottom, we have Gonk, which is our version of Linux and a couple other low-level things that are really boring. And on top of that is Gecko. Gecko is Mozilla's rendering engine. That's the thing that displays the web. And then on top of Gecko, there's Gaia. Gaia is this HTML5 experience that we talked about. So all the things that you see in Firefox OS are all implemented in HTML5, and that's what we call Gaia. So the simplest way to implement this would be, of course, to take a Java VM, symbolized here, so the inventor of Java, and we could just kind of like stick that on top of Gonk next to Gecko, and basically just kind of wedge it into our phone. And then we could run messaging things on top of that. Of course, this is bad, at least for two reasons. First of all, Java has a really bad track record with security. They're still finding really fundamental bugs in Java, and they're often really bad because they affect all browsers at the same time. So if you do this, if you take a Java VM and kind of like stick it into our system, since the Java VM would be sitting directly on top of Linux and the OS core, we would basically create a second surface for vulnerabilities. There could be like additional bugs in the Java VM, and they would create additional room for the phone to be broken into. So that's a really bad idea to kind of put it in addition to the rendering engine. We basically have twice as much opportunity for something to go wrong. And then the second reason, of course, is that it would be really bad karma to put another Java VM into the web stack, right? So we got to the point where you don't want to need Java on a desktop. And with feature phones over the next couple of years going out of fashion, Java will also go out of fashion with it. So at this point, putting a Java VM into a web-based and standards-based and HTML5-based phone seemed like a really bad idea. So we decided not to go that route. So of course, what that leaves us with then is to take our little diagram here with the Japanese characters and the ice cream cone and simply take a Java VM and put it on top of the entire system. So we simply write an app in HTML5 that implements a Java VM, and that app knows how to download the messaging app itself, and I can run this whole thing on an existing phone. The really nice part of this is that at the time that we started this, which was about 4 or 5 months ago, we already had a large number of phones out in the field that all don't have the original version of some of these messaging apps. If we do it this way, since we're not using any privileged HTML5 capabilities, we're not kind of trying to bypass the platform in any way, we can actually make an app, an HTML5 web app like this, and just put it in a marketplace where people can download it and they can use this without having to buy a new phone. So this is very nice because we address the existing set of phones as well. All right, the downside of it, of course, is now we have to write a Java VM in JavaScript. That's very exciting. As I said, my background is in writing compilers. That's what I did in academia before Brendan kind of freed me from academia, let's put it this way. And my entire background actually was in Java compilers before I started to do JavaScript compilers. So this is one of the reasons that I found this project particularly interesting, because I have done both extensively. I have written several Java VMs, and I have written several implementations of JavaScript compilers. I never really tried to write a Java VM on top of JavaScript. So that seemed very appealing to me. So for the next couple of slides, I will dive a little bit into technical details and explain to you at a high level how Java works and show you some of the problems that I ran into trying to build a Java VM that's really ready to run production-level code on a device like this. Don't worry too much if you don't see or understand some of the details. For example, there will be no quiz after my talk on the details of this slide. This is merely meant to kind of highlight some of the concepts you need to understand so you can understand the next slides. So on this slide here, really the only thing you should memorize is that Java is built from class files. Every Java program that you get consists of a large number of class files. And each class file represents one class. And these things are stored in a binary format. It's basically an array of bytes that contains information about the class itself. It contains the fields and the methods of the class, the actual code, which is stored as a bytecode. The bytecode you can think of as a sequence of bytes that explains what instruction the VM should take. And the VM goes step by step through these bytecode instructions. So really all you have to do to run a Java program is you have to find a way how you can parse these class files, and then you write an interpreter for this language, this Java bytecode language, and then you run that interpreter over the code that you find in these classes. And once you have one class, that's your starting class, it will call methods. It can call methods in the same class, or it can call to other classes. And whenever it calls to another class, you have to go and find the class file for that other class. So that's the entire magic behind Java. Now, as I said, the Java programs consist of a large number of these class files. A popular messaging app like WhatsApp or Viber is often hundreds of different classes. In addition to that, you also have library classes, which are often thousands of classes. It would be, of course, kind of awkward to have to carry around 1,000 files if you're installing a Java program. So what they came up with is jar files. A jar file is a Java-like name for a zip file. So it turns out jar files really are like zip files. They're exactly structured the same, and they're basically just a zip archive with all the Java class files inside of that. And if you want to distribute a Java app, all you do is you give someone a jar file, and then the VM can go and read all that stuff out of the jar file. The first problem we run into is that, as I explained, what we want to do is we want to write an app that knows how to run a Java program, and it will get that actual Java program from whoever is distributing the Java program, not from us. So the first step we have to make sure of is that this Java VM that we are writing can read these original jar files. So we need to be able to parse zip files. Fortunately, that's something I had to do before. So we did PDF.js a couple years ago to display PDF documents with HTML5. And there as well, the first problem we had to solve is that PDF documents are basically zip files as well. So you can see a meme here, like everything out there is a zip file, basically. And we had actually implemented for PDF.js a zip file reader that's up on GitHub. And I had that lying around there for like the last 2 years, and we didn't touch it since then. So I took zipfile.js and I wrote a little parser for class files to kind of see how this goes. And it should work great, right? We can parse class files now, we can read zip files, and it totally didn't work at all. That was somewhat unexpected. So I spent a good afternoon trying to find out why the class files I was getting out of the jar files did not make any sense. And it turns out that if you read the specification of zip files, which I did, it's just a very painful process. I hope you never have to do that. It sucks. The specification says that any zeros at the end of a stream, you don't have to store. So if you're storing a compressed file and the last couple of things in the file are zeros, you can leave out those zeros. The program that parses the zip file is supposed to know that if there's something missing, just add a 0. And I somehow didn't read this right the first time we wrote this implementation. So what the code originally did is if you're running out of bytes in your typed array and you get an undefined back, you raise an exception. So this is the error we were running into. And the fix, of course, is very easy. We simply read data from a byte array, and then we just or a 0 in there. This is a trick we will use a little bit later on a slide as well. What this basically does, it forces that to be an integer number, and undefined is the equivalent of the integer number 0. So whenever we read past the end of this byte stream, then we will start reading back zeros, which is exactly what the specification calls for. The neat part is that we shipped this bug in PDF.js for years. So people have looked at like billions of PDF documents, and nobody notices that this was wrong. This must be because the implementation of jar files and of PDF readers is separate. So the PDF readers or generators don't seem to generate this kind of optimization with 0 at the end. So since then, we actually fixed that in Firefox as well. All right, next step. So I had now a way to read jar files after some pain, and I had a way to parse class files. The next step, of course, is a VM. We have to go and get something that will interpret that bytecode and run the actual Java program for us. The most natural way of doing that these days would be, of course, to take mscripten. Mscripten is this C++ or C++ compiler that takes existing C++ code and it emits through LLVM and a couple other steps JavaScript from that. Over the last year, actually, we also did an extension of that called asm.js, which I think Brendan will show in his talk in a little bit, that makes it possible to make this really efficient. So if you do this path, if you go from C++ down to JavaScript, you can get really, really close to native performance. So if this worked, this would be great, because all I have to do is take KVM, which is written in C, and I could compile that, and I would have a VM in my browser or in my rendering engine. In theory, that's really great, and you should always reuse code if you can. However, in this case, I couldn't find a license for KVM. And I'm serious, there's no license. They put out code there, they're saying that there's no license, and they don't have a license for it. So I started calling up some old friends from Sun, and there's really no license out there. So for some reason it's out there, there's no license right now to use it, and I couldn't find anyone left at Oracle who knows how we could slap an open source license onto it. So I ended up basically not being able to use KVM because it's not allowed. You can only use it for research purposes. You cannot use it for any other purpose. So this was very sad, because there's essentially no other open source project that implements this specific flavor of the VM. There's a couple open source VMs that implement the more heavyweight, complete Java VMs, but nothing implements this limited configuration that KVM needs. So one of the reasons I'm here today with you is because Sun didn't put a license on KVM 14 years ago. All right. So to write a VM, I went on GitHub and tried to find who else tried to do this. And it turns out a whole bunch of people have tried to write Java VMs in JavaScript. And everyone tends to do that for about 2 months before they give up. So I looked at all the different implementations that were completely incomplete. And the one I liked the best is called Node.js. I liked it because the code structure was maybe very nice and neat. Or maybe just because his style matched my random style very well. But anyway, this was the one that I started with. It had a class file parser and a bunch of different other pieces that I was able to reuse. So with this, actually, I was able to get the first Hello World program to work. I very quickly realized that the way that they implemented natives is a really bad idea. So what is a native in Java? As you probably know, Java is a type-safe language. So there's a lot of things you cannot do in Java. You cannot poke around with memory addresses. You cannot directly call a system call that would invoke some service from the operating system. To do these things, Java has to somehow call into C code. And this C code is what Java calls native code. It's basically in the VM a way to recognize that you're calling a special magic method with a specific name, and that name is mapped to running a C function instead of trying to run actual JavaScript bytecode program. The way that the author of this VM implemented all the Java libraries is that he basically made every single Java library method a native method. So he would go ahead in JavaScript and implement every single thing that you need in Java in JavaScript. That, again, is a bad idea for a couple different reasons. First of all, there's a lot of stuff. The Java library that you need for these phones is actually not very large. It's about 1 megabyte as a compressed jar file. If you uncompress that, and because class files are actually very compact, there's actually a ton of code. It's a couple thousand classes. And those classes have a lot of different implementation details. My life is too short to write all of that again in JavaScript 14 years later. And again, I also kind of felt bad karma to redo all this work that was done 14 years ago. So of course, a much better idea would be, even though we cannot use the same VM that Sun did 14 years ago, we could at least use the same libraries, maybe. And this is where we got lucky. And I'll come back to it in a second. The second piece, the second reason it's a really bad idea to try to write a Java library in JavaScript is that even though the name is very similar, and I'm sure Brendan has a couple more jokes on this one too, the name is very similar, but semantically these languages are very, very different. So in Java, for example, if you invoke a method and give it an object that is null, something very specific happens in Java, and you're supposed to raise a Java exception. So what the VM has to do, basically, is not just throw an underlying JavaScript exception, but the VM has to throw a Java exception, has to take a different path running bytecode, and it has to give the program a chance to react properly to that null exception. And because Java is so old and has gone through so many rewrites and so much code was written for it, Java applications tend to often really rely on these very subtle little details. So when you're starting WhatsApp, for example, it does rely on the proper handling of a null object dereference. If you start VChat like this, it relies on an integer division by 0 being thrown as an exception and being reported. So it would be very difficult to rewrite all this JavaScript code, all this Java code in JavaScript, and make sure that every single step you maintain precisely the semantics of Java. It would be, of course, much better if you can simply take the library code as Java and then we simply run that in a VM. Then we don't have to write the code, and we have guaranteed the right semantics. So as I said, we got lucky here because Sun open sourced the library parts of Java, just not the KVM itself. So we could simply download from Sun's site the entire source code of the library that you need for these phones to work. That saved a ton of effort right there. That's great. All right, let's talk a little bit about the VM. So now we have basically all the basic pieces. We can read jar files, we can look at class files, we have the library stuff as bytecode. Now we need a VM that can actually run this code. The VM itself is really straightforward. As I said earlier, Java bytecode is just basically a sequence of bytes. There's instructions in there encoded. There's a little bit less than 255 instructions. They're numbered, and there's a definition that says if you see 0 in your byte stream, that's a no-op. Don't do anything. Just go to the next instruction. If you see 1, it pushes a null constant onto the Java stack, and so on. So the most trivial way of implementing this is simply you go ahead and you write a little interpreter. It grabs the current frame, and it pulls out the stack, and then it does operations on it in an infinitely spinning while loop. It's interesting to look at two parts of this loop, or this instruction execution. The one I'd already showed briefly a couple of slides earlier. In Java, you have strict typing. So in Java, actually, you have different bytecode instructions for adding to integers or adding to long integers. Integers are defined as 32-bit integers, and longs are defined as 64-bit integers. So for integer addition, what you have to make sure is that when you add two numbers, they're always guaranteed to come out as an integer again. Now, we could make sure that the number that goes into stack pop on those two, they're always integers. However, if you add two integers in JavaScript and it's larger than a 32-bit integer, what you get is right? It just overflows into doubles. So JavaScript doesn't have this weird case of Java where if you go over the definition range of an integer, you kind of come back out on the other side of the world. Where, like, if you add 1 to the largest 32-bit integer, then you get a negative number. So that's really nice for JavaScript, but in case of a Java VM, we have to actually emulate the way Java reacts here. Otherwise, if some program relies on this, it wouldn't work anymore. We use the same trick here. If you OR a number with 0, you force it to be converted to an integer number. And that way, we can implement the integer semantics of JavaScript. The second one is a long addition down there, and that's actually a bit harder because JavaScript cannot directly calculate 64-bit numbers. You have only doubles, and a part of the doubles is reserved for essentially telling the system where the period goes. So as a result of that, we are using glong.js, which is the 64-bit math library that ships with a Clojure compiler. So all longs that are generated on the stack are basically wrapped into those objects that allow you to do 64-bit computation. Fortunately, on these feature phones, 64-bit math is very rare. So it's important to support it, but it's not really a performance problem. A more interesting instruction is getField. And for those of you who don't like reading code, I promise there's only 2 or 3 slides left before we go back to memes and things to laugh about. I wanted to show a couple more examples of stuff that was really interesting to implement. And as I said, I've written several Java VMs at this point, and implementing some of the more complex features of Java this time around in JavaScript turned out to be very, very different from any other implementation that I've done. A good example of it is getField. What getField does, it gets the value of a field of a Java object. Basically what it does is it resolves the field into a slot into the object, and then tries to read from that slot in the object. The Java specification defines certain error conditions that can happen. One example is if you give getField a null object, then it is supposed to throw an exception. So as the interpreter is running, if object happens to be null, then this raise exception and yield is going to be invoked. So let's look at that for a second, because that's somewhat interesting the way we did that. So what raise exception and yield does is essentially it raises an exception, and I will show you in a second what it does. And after that, it does a yield by throwing a JavaScript exception. So again, we are trying to throw a Java exception by doing some code and then throwing a JavaScript exception. If you can still follow me at this point, you're really brave. The reason we are doing this is that Java is a fully synchronous language. This is very different from JavaScript, where really one of the prime directives of JavaScript is try to run as little code as possible in your event loop and don't hog the event loop. Run small snippets of code and allow the system to run events as well. The way we implement this discrepancy is that we have an outer loop that you can see here in context prototype execute. And it's basically a loop where if the code that we run in VM execute throws this specific exception of VM pause or VM yield, what this code does is basically it jumps up and goes back to the event handler, returns to the event loop, and the next time we come around, we will run code again. So this is essentially how we implement the ability to take a Java thread, and at any time we can deschedule it so the system can do something else. And of course, this is also how we implement multitasking. Java is a multi-threaded system. All we have to do is basically have several of these things posted, and then you essentially have several threads that are running at the same time. All right. I promised that you will look at raise exception, and don't worry, most of this is not interesting. The only piece that is really interesting is the very bottom of this. If you look at the integer array, the uint8 array that we are generating there, what you're actually seeing there is that we're hand assembling some bytecode inside that method. So when we're trying to raise an exception, it actually turns out we cannot directly raise the exception. Instead, we're generating a fake Java method that we put onto our Java stack that we're implementing in JavaScript. The reason we have to do that is that there are several steps necessary to throw an exception. And each of these steps can fail individually. The only way I can handle that, for example, the only way I can properly handle throwing an exception while throwing an exception is if I have a second method in between there. So what, for example, can happen is, let's say you're trying to throw a specific exception with a name X, and that name doesn't exist. Then in that case, the VM would throw an exception telling you that a class could not be found. And when you're throwing that exception, you might run out of memory, in which case the VM is going to throw an out-of-memory exception. So you have to have this cascading. We are solving this with this synthetic methods that we are throwing in between the stack. This is very neat because the simple structure of JavaScript allows us to do this very efficiently, because we're using these uint8 arrays to actually store the stack frames. I mentioned a couple of minutes ago the concept of natives. Natives are in Java a way to call to the operating system or the underlying code. In JavaScript, of course, there's no notion of that. We simply call in the DOM or into functions that are implemented in a JavaScript library. So really for this VM, native methods are essentially implementations of code in JavaScript instead of C or C++, of course. There's a fairly simple way to implement this. What we essentially do is when you're calling a method, you supply the name in the bytecode. And we have a little override list where we look into, do we have a native with this name? And if so, we execute that JavaScript code instead of trying to call a Java method in the interpreter. So you can see a couple implementations here where we essentially just call some native JavaScript written code that implements those Java functions. All right. Almost done. One thing we did not expect is that just how slow this would be. So if you get onto this point, we were about 100 times slower than the application running on the feature phone. And that was really unexpected. Because most of the time, if you look at Java, it really runs a lot of the complex operations in native code. The reason for this is that back when Java was first written, there were no compilers yet for Java. So a lot of the Java programs could not do a lot of heavy computation in Java itself. So the Java language started to provide a lot of native C implementations of very complex functionality to compensate for the fact that Java was so slow. So we really expected that even if you have a slow VM for Java, we should be a little bit closer to usable than 100x away. It turns out that the main reason for this being this slow is that there's some very frequently called things in any programming language. Let's say comparing two strings. This is called in Java equals. In Java, all these things are implemented in Java itself. So if you're comparing two strings, you have to call this function here. And don't worry, I will not try to read through this, what this does. All you have to remember is that there's like 80 bytes or so of instructions in here, and I highlighted with red a loop that's inside of this. So what this code does, it does a whole bunch of checking whether it's really a string, and then it goes to that loop, and for every single character, it individually compares whether it matches the other string or not, and then returns true or false. And of course, each of these steps in this program, or Java VM, written JavaScript, has to interpret. So comparing two strings in this Java VM we just wrote is horribly slow. We did a little profile using the dev tools, and we could immediately see that most of the time was spent in 5 or 6 functions like this. So a very easy way to fix that, of course, is to use the same mechanism we just saw with native methods. A native method, again, is something that we implement in JavaScript instead of in Java. So we can simply take shortcuts. So I have a little native method that overrides the pure Java implementation, and it goes ahead and simply checks that it's a string, and if so, it does a string compare at a JavaScript level. That's, of course, massively faster because the JavaScript VM in the browser knows how to do that very efficiently. You don't have to circle that interpreter loop all the time. So after they did this work, of course, we expected things to get a lot better. And they get a lot better. It got like 10 times faster or so, but it was still kind of painfully slow to use. And the reason for that probably is that actually Java has advanced quite a bit since its early days. And today, most of the time when you run Java programs, you actually also compile them over to x86 or ARM machine code. So even on these simple feature phones, there's actually a compiler built in that takes the bytecode, and then instead of just running an interpreter, it generates machine code from the bytecode and then runs that machine code. And since we still had an interpreter, we were slower than these feature phone systems, to the point where the app was not really usable. So the next step, of course, is how to compile Java in JavaScript. And this seemed like a really daunting task for anyone who has written compilers. So for those of you who had the curse or privilege, whichever way you want to see it, to ever have written a compiler, generating code in a compiler is like the most painful part of compilers, because machine code is so hard to read and very hard to target. And it's also the most exciting thing to debug. Like you have not debugged in your life until you have trying to debug some machine code that goes wrong on you. And you're trying to understand what the hell happens there in some binary machine code you're looking at. So when we got to this point, this seemed pretty scary, quite honestly, because every time I had done it before, it was a really daunting task to deal with. Fortunately, this is JavaScript, right? And it is not machine language, it's not x86, and it's not ARM. And it's a lot easier to do this in JavaScript, and this was almost unexpected for us. If you look at the compiler that is in j2me.js, that is probably the smallest Java compiler I've ever seen. And if you think about it for a moment, what it does, it takes a Java code and, of course, emits JavaScript code from it. It all of a sudden, of course, makes a lot of sense that it's a very small compiler, because what we're doing is almost like an inversion. JavaScript is actually a much more semantically rich language than Java, and has much more powerful primitives. What we're doing is we're basically taking Java and we are lowering it to this much higher representation. This is, of course, very easy, because many things where you have to painfully assemble in machine code instructions for Java are very, very trivial to do in JavaScript. We also harnessed a couple other tricks. To make this process particularly easy when you're trying to compile Java over to JavaScript, we try to use as much of the JavaScript semantics itself. So for example, Java objects are represented through one JavaScript object. We're not trying to implement our own garbage collector. We are not trying to implement many other pieces of the Java VM that traditionally you have to implement in some native language. So by making our Java implementation match very, very closely what the JavaScript language does, the actual compilation approach itself becomes really trivial. So this is what compilation looks like, and this will look eerie familiar to you if you remember the execute loop. It essentially does the same thing that the execute function did. There's a compile function. You go over the bytecode in sequence, and for every bytecode operation, you simply emit some code. And code in this case is simply a string that we define up there, and we concatenate into that string operations in JavaScript that basically emulate the stack nature of Java and execute the operations that Java is executing. So this turned out to be really a very easy way to compile code. This part was really easy but what's a lot less easy is actually trying to run that code. We are running the stuff in an environment where content security policies are enforced. And if you don't know what it is, I recommend you go and read right after this talk, because it's very important that you know what it is. For those of you who don't know yet, CSP is a way how you can restrict web applications from doing dangerous things. And eval is one of those things that's pretty dangerous, because if you have stuff coming in from the user and it somehow gets into eval, that's usually where things go wrong and someone is going to take over your code and inject some code. So we are in an environment where we can actually not use eval. So we can compile a Java program just fine to JavaScript, but then we cannot actually eval it because the eval function itself is disallowed. I unfortunately don't have time to go all the evil details that it takes to bypass that, but essentially what we are doing is we are firing up a new iframe, and we load the code in that new iframe. And that iframe kind of posts messages us back and forth as we execute code. And it actually even works. So this was even surprising to me. One of the other authors, Nick, on this project came up with this idea, and it's pretty insane. If you really would like to see some fun code, I recommend you take a look at that. All right, now we're at the demo part of this. It seems that the convention is when Mozilla comes to demo, or at least when a Mozilla CTO comes to demo something at a JSConf conference, you have to show some sort of live demo. And Brandon already set a precedent that it is a game that you're playing. There is no Quake for j2me, as far as I know. So I picked the second closest thing I could find. And this is a live demo, so if it doesn't work, I'm very sorry. Let's see, where are my bookmarks? There we go. So this is the Asteroids Java game that is common on these phones. And great, the resolution is screwing me here. I cannot get to my start button. Let's see, that's great. It's live debugging here. All right, now it works. All right, so I can go to menu here. So this is all the Java stuff that's running. This is the interpreter loop running here, running this Asteroid game. This is a jar file. This is actually an open source j2me game you can find on the web. It's on GPL. It's really great if you have to debug a VM, if you have a program you have the source code for. Try to debug with something where you only have the bytecode for. That's really painful. So here, these are touch events from the browser that are sent over to the Java VM. And I can go ahead here and start this. Everything you see here, like this very ugly yellow UI, this is all rendered in Java, in like 14-year-old Java code that runs on these phones. And I can start this, and then live demo, I cannot move my ship. So this is unfortunate. Let's see if you can do this if you start this again. No, I still cannot. All right, I cannot tell you why I cannot move my ship right now. It worked in a room there. You can believe me or not. But in theory, I would give you a live demo right now. Next time, I'm definitely going to record this and not show this live. All right, let's go back to our slides. All right, before I run out of time, first of all, thank you very much for listening to me going on about Java and JavaScript and VMs written in JavaScript. I would like to acknowledge a couple of people that have worked on this project. As with many of the other projects that I started in the past, it's usually me who gets to do the first fun couple of weeks. And a bunch of people have to come in who have to do months of hard work to actually make it work. So there's a whole bunch of people from Mozilla and also outside contributors to help the j2me get it to the point where it can run Java applications. And I recommend you look up their names. And if you're interested in the code for this, it's all up on GitHub. And check it out and run some j2me stuff in your browser. Thank you very much.